Okay, here we have, let's just look at what's the equation for electric field. So what we'll remember from force of gravity, we saw force of gravity is equal to mg, which is equal to gmm over r squared. So if you want to find the gravitational field strength, we get G is equal to gm over r squared. So it's very similar with this one. You can see that the electric field, E, is kq over r squared, so just without that extra q there. So if you want to go back and forth, we can see there's this equation, E is equal to F over Q. That's very similar to saying force is equal to mass times gravity. This one we just have force is equal to Q times our electric field. So these two topics, gravitation, electrostatics, lots of overlap. It's very similar equations, just instead of like capital G, we have K. Instead of masses, we have charges. So how this works, if I have a positive charge, again, we have these electric field lines that are going to go away from the positive charge. Going away from the positive charge. And how this equation works, if we put what's called, we call this a test charge. Basically, it's just a positive charge. It's just, this is our little q. Yeah, that's our little q. This is our big Q. We call this a test charge, and it's going to head off in that direction like so. So a test charge. Okay, so it's going to, electric field lines tell us the direction a positive charge will travel. So let's go down and do an example. So the question is asking us, calculate the magnitude and direction of the electric field at point P, which is 30 centimeters to the right of a point charge Q, which has a value of negative 3.0 times 10 to the negative 6 coulombs. Let's draw a picture. So we have a negative charge, and we're saying what is happening at some point that's 30 centimeters to the right. So we're saying what is happening at some point P. So before we do these, we should always just draw a picture and make sure we understand what's happening. We know that a negative charge is going to have electric field lines that are pointing towards it. Always ask yourself that, remember, the field lines tell us the direction a positive charge will travel. So ask yourself, will a positive charge go towards it or away from a negative charge? So at P, we know that it's going to experience an electric field to the left, like so. So just calculate that. We get E is equal to KQ over R squared. So we get 9.0 times 10 to the 9 newtons meter squared per coulomb squared. And multiplied by our charge, which is 3.0 times 10 to the negative 6 coulombs. And it is a distance of 0.30 meters squared. So I didn't actually put the sign in there. Again, because there's so many positive negatives, like it's a positive and a positive, negative and a positive, negative and a negative, or just all is it to the left of the object, to the right, above or below. I find it a lot easier just to solve for the magnitude. So 9 times 3 divided by 0.3 squared, taking account those powers, we get a value of 3.0 times 10 to the 5. So solve for the magnitude first, and then you look at, let's take a step back, look at the scenario again, and we say, oh, it's an attractive force. So 3.0 times 10 to the 5 newtons per coulomb, and this is to the left in this case. So that is our answer, or towards the negative charge. You can also write down towards the negative charge. And what this is telling us is that, so 3.0 times 10 to the 5 newtons per coulomb, it's saying that if I were to place a charge at location P, it's going to experience 3.0 times 10 to the 5 newtons for every coulomb of charge. So if I put a 1 coulomb charge there, it's going to experience a huge amount of force. So around 300,000 newtons of force. But usually what happens is very rarely do we have really large charges. So we're talking about things like electrons, which charge to the negative 19 coulombs. Like usually charge is very small. It's only when you have tons of electrons there together then we get large charge. But it's saying for every coulomb, we'll get that quantity of force.